So today let us start with some problems on the factorization of polynomials and the zeros of polynomials. So the first problem we are going to do today is this. Let f of x is equal to a0 plus a1x plus dash dash an xn belongs to f of x, and a different from 0, a belongs to f, be a 0 of f of x. Then then 1 by a is a 0 of the polynomial g of x is equal to a0 x to the power of n plus dash dash plus an. See this, these two polynomials are different, the coefficients are reversed, and the thing which we need to note is a is different from 0 and a is in f. So it's actually a very simple problem. A is a 0 of f of x implies f of a is equal to 0, and that implies a0 plus a1 times a plus dash dash an times a to the power of n is equal to 0. And because a is different from 0 and a is coming from a field, it has a multiplicative inverse. So 1 by a exists. So this we'll call it as equation number 1. So multiply 1 with 1 by a to the power of n, and that is 1 by a to the power of n, which is possible because a is different from 0, and that implies a0 times 1 by a to the power of n plus a1 times 1 by a to the power of n minus 1 plus dash dash an is equal to 0. And this implies g of 1 by a is equal to 0. And that implies 1 by a is a 0 of g of x. It's a very simple problem. Just want to make sure that the idea of zeros of a polynomial is clear. Let us do one more problem. Let alpha belongs to f and f of x belongs to f of x. Then the remainder of f of x when divided by x minus alpha is f of alpha. So f of x is equal to x minus alpha. We can write f of x as x minus alpha times q of x plus r of x by the division algorithm. where Q of x and R of x belongs to f of x, and the degree of R of x is less than 1, because we are dividing by x minus alpha. And that means R of x is a constant polynomial. And that means f of x is equal to x minus alpha times q of x plus c, where c belongs to f. Now replace x by alpha. F of alpha is equal to 0 plus c, and that means c is equal to f of alpha. That implies f of alpha is the remainder when f of x is divided by x minus alpha. Our next definition is going to be one of the important definition in the study of polynomials over a field. It is similar to the prime numbers in set of integers. Prime numbers are integers that cannot be factorized, meaning the only factors of prime numbers are 1 and that number. That is how we define the prime numbers. So we are going to define the similar concept in the ring of polynomials. So let f of x belongs to f of x, where f is a field. Then f of x is a irreducible polynomial in f of x, or f of x is irreducible over f if f of x cannot be expressed as a product of two polynomials g of x and h of x in f of x, the degree of both is less than the degree of f of x. So if you write f of x is equal to some constant times g of x, this is not the condition that we are looking for, because here if this is a constant, the degree is 0, that means the degree of g of x is same as g of f of x. That is not what we are looking for. It has to be two polynomials of lower degree than this degree of f of x. One example is x square minus 2 in q of x is an irreducible polynomial over q. well, I need to extend this definition. If the polynomial f of x is not irreducible, then it is called a reducible polynomial. In f of x. So this is an irreducible polynomial in q of x. But x squared minus 2 is not an irreducible polynomial in R of x, because you can still factorize this one as x square minus 2 is equal to x plus root 2 times x minus root 2. These are of lower degree than this, but these are not elements of q of x, but they are elements of R of x. So this is an example of an irreducible polynomial in q of x, but not in R of x. Now let us do a very simple theorem on polynomials of degree either 2 or 3. So it's a very simple theorem. Let f of x belongs to f of x, and degree of f of x is equal to 2 or 3. Then f of x is reducible in f of x if and only if it has a 0 in f. See, if you take that example of x square minus 2, the 0 of, if you consider this to be a polynomial in q of x, the 0 of this polynomial are not in q. 0 of these polynomials are root 2 and root 3. Sorry, root 2 and minus root 2. Those are not in q. And that is why this is an irreducible polynomial over q. So let us prove this. This is a very simple proof. So there are two parts because this is an if and only if condition. So let us assume that f is reducible. Let f of x be a reducible polynomial over f. And that means f of x is equal to ax plus b times another polynomial. Because this is of degree 2 or 3. So if it is reducible, the degrees of the factors, one of the degree of one of the factors has to be 1, and this is how you write a linear polynomial, a polynomial of degree 1, where a comma b belongs to f. So this implies that, see, this is actually and here you can say and a is different from 0, and b is also different, a is different from 0. Okay, because if a is equal to 0, then this will become a constant polynomial. But that is not what we want, it is a reducible. So this implies minus b by a is a 0 of f of x, and minus b by a belongs to f. So if it is reducible, it has a 0 in f. Now let alpha be a 0 of f of x. That implies x minus alpha is a factor of f of x, and that implies f of x is reducible in f of x. Let alpha in f be a 0. So this is a polynomial in f of x. So if it's a polynomial, if a polynomial in f of x is a factor of this, definitely f of x is reducible, because the degree of this is greater than 1. Greater than 0, sorry, greater than 0. Now let us do a very simple problem to illustrate this theorem. Let f of x is equal to 2x cubed plus x square plus 2x plus 2 belongs to z5 of x. We need to find out whether this is reducible or not. So f of x is reducible, or we'll write that the degree of f of x is 3. So f of x is reducible only if f of x has a 0 in C5. And what is C5? 0, 1, 2, 3, 4. Okay? So f of 0 is going to be 2. F of 1, this is 2 plus 2, 5, so this is equal to 2. Right? F of 2, this is 16, and this is 4, this is 4, and this is 2. So this is 0, 8, 8 is 3. So f of 3 is equal to f of minus 2, because 3 is minus 2 in C5. So this is going to be minus 16, this is going to be 4, this is going to be minus 4, and this is going to be 2. So this is actually different from 0. I'm not going to compute that. Similarly, f of 4 also is going to be different from 0, because f of 4 is actually f of minus 1, and that is also different from 0. So f of x does not have a 0 in Z5, implies f of x is irreducible in Z of x. We'll do one more problem using this result. Find all irreducible polynomial of degree 3 in Z2 of x. So any polynomial of degree 3 in Z2 of x is of the form x cube plus ax square plus bx plus c, where a comma b comma c belongs to Z2, which is nothing but 0 and 1. The coefficient of x cube has to be 1. It cannot be 0. If it is 0, then this won't be a polynomial of degree 3. So the possible polynomials are x cube plus x square, x cube plus x square plus x cube plus x square plus x plus 1, x cube plus x plus 1, x cube plus 1, x cube plus x square plus 1. That's it, right? So here this is definitely reducible polynomial because f of 0 is 0, here also f of 0 is 0, here also f of 0 is 0. This one, if you put 0, so this is not irreducible. So these are not irreducible, okay? Here this one, if you put 0, it is not 1. But if it is 1, 1 plus 1 plus 1 plus 1, so this is 0. So this is also not irreducible. These are all reducible. This one, if you place 0 instead of 0, x, this is going to be 1. But if you place 1, that's also not equal. So this is actually irreducible. This is actually not irreducible, this is reducible, because if you put 1, 1 plus 1, 2, which is 0, so 1 is a 0 of this polynomial, and therefore this is reducible. This also is irreducible. So there are only two irreducible polynomials of degree 3 in Z2 of x, and they are x cube plus x square plus 1 and x cube plus x plus 1. Only these two are irreducible. We will do one more problem using this result. Find the number of irreducible polynomials of degree 2 in Zp of x, where P is a prime. So the approach is going to be like this: number of irreducible polynomial is equal to total number of polynomial minus number of reducible polynomial. Right? So the total number of, so any polynomial of degree 2 in Cp of x is of the form ax square plus bx plus c, where a is different from 0 and a, b, c belongs to z. Right? So the total number of polynomials is equal to p times p minus 1 times p minus 1. Right? Because, or no, it is the other way. This p minus 1 times p, and that is equal to p square times p minus 1. These two can be any number in Cp, but a should be a non-zero element from Cp. Now we need to find out the reducible polynomial, number of the reducible polynomials. So let us take an example here. Let f of x is equal to, we will make a is equal to 1. So x square plus, let us say, ex plus f belongs to Zp of, I don't want to confuse f, let us take g, where this belongs to Cp of x. That means e comma g belongs to Zp. Okay? If this is, we want to find out the number of reducible polynomials. So if it is reducible, this should be written as x plus c times x plus d, where c comma d belongs to c. Then only this is going to be a reducible polynomial. The way the number of ways this can be written as, so here c and d can be different, or c and d can be same. The number of ways c and d can be different is p times p minus 1 by 1 time, using the permutations, and that is p minus 1 by 2. Number of times c and d are equal is equal to p. So the total number of quadratic polynomial of the form, total number of quadratic reducible polynomial of the form x square plus bx plus c is equal to p plus p times p minus 1 by 2. Right? is actually that is equal to p plus p minus 1 by 2. So that is equal to p plus p times p minus 1 by 2. If you take p outside, 1 plus p minus 1 by 2, and that is equal to p plus 1. That is the total number of quadratic reducible polynomial of the form x square plus bx plus c. But this is not the only form of quadratic polynomial in Cp of x. You can have 1, 2, 3 up to p minus 1 here. So the total number of reducible quadratic polynomial in Cp of x is p minus 1 times p plus 1 by 2. So total number of polynomial is what? The total number of polynomial is p square times p minus 1. So the total number of irreducible polynomial is p square times p minus 1 minus p times p square minus 1 by 2, or you can say p plus 1 times p plus 1. So if you take p on p minus 1 outside, this is going to be p minus p plus 1 by 2, and that is p minus 1. This is 2p minus p. This is 2p minus p. So this is actually p minus 1 by 2. That is p times p minus 1 whole square. So there are these many irreducible polynomials in Cp of x. Now let's do a very important theorem. Let f of x belongs to C of x. Then f of x can be factorized into two polynomials R of x and S of x of degree less than f of x and in Q of x. See, there is a difference here. This is a C of x and this is Q of x. This R and X of x are in Q of x, but f of x is in C of x. If and only if this is possible, if we can factorize f of x into R of x and X of x in Q of x, if and only if f of x has such a factorization in C of x of with the polynomials of same degree as R of x and S of x. Now let us explain this the situation here. I have an example here. 42x square plus 19x minus 6. This is our f of x, and that definitely belongs to C of x. Okay, so f of x belongs to C of x. Now the theorem says that this can be factorized into R of x and S of x in Q of x if and only if it has such a factorization in Z of x. So this can be factorized into 7x plus 14 by 3 times 6x minus 9 by 7. If you multiply this, you will get this. Okay? These two are elements of Q of x. Not in Z of x. Because they have got fractions here. This is possible only if there is such factorization in Z of x. This can also written as 3x plus 2 times 14x minus 3. If you expand this one, you will get this. But these two are Z of x. Okay, so that is what the theorem says. And here, one part is simple. The only part is the other way. So let us start with the easy one. If f of x can be written as g of x times h of x, where, or let us say, okay, h of x, where g of x and h of x belongs to C of x, then that implies g of x and h of x belongs to Q of x, and we are done. Meaning, if you find this one first, this is a polynomial in Z of x, at the same time this is also a polynomial in Q of x. So if you can find the factors in Z of x, that is automatically in Q of x, and that's what this says. Next thing is, if f of x is equal to g of x times h of x, or you can say R and S, where R of x and S of x belongs to Q of x, that is this, we found this one, then we need to show that there exists g of x and h of x in C of x such that f of x is equal to g of x times h of x, and the degree of g of x is equal to degree of r of x, and degree of h of x is equal to the degree of s of x. See, the degree of 3x plus 2 is same as the degree of this, and here this is same as this. So this is the part it is going to be little complex. So in order to prove that, we need a couple of definitions and a result. So first we will start with the definition here. Let f of x belongs to f of x, and f of x is equal to a0 plus dash dash a n x n. Then the content of f of x is the GCD of a0 dash dash a. Another definition is, if the content of f of x is 1, then f of x is called primitive. Example, let us take a polynomial like this, 2x squared minus 6x plus 8. This definitely belongs to C of x. So the content is, or content of f of x is GCD of 2, 6 and 8, and that is 2. Okay, we will exclude we are not considering the sign of this, so it's going to be the GCD of this. If you take another example, g of x is equal to 2x squared minus 3x plus 1. So GCD of g of x is equal to GCD of 2, 3 and 1, and which is 1. So this is a primitive polynomial. That's what it means. Basically, what it means is, if there is a common factor other than 1, that is the content. If the common factor is just 1, and it is primitive, it is primitive. And there is a result which we need to show for our theorem, and that is this: g of x and h of x are primitive implies g of x times h of x is primitive. The proof goes like this: let P be a prime number that divides the content of g of x times h of x, and that is equal to f of x. See, what we are trying to do is, if it's already 1, then it is primitive. Assume that it is not 1. So it's going to be greater than 1. Then we'll take a prime factor of that GCD, and that is this. Now we'll define a homomorphism. Define a homomorphism from z of x to zp of x by, let us call it as phi bar, but with the phi of, with another function phi z to zp as z of n is equal to n mod. See, the definition of phi bar is like this. This is a polynomial. If you take a polynomial here, replace the coefficient with the n mod p as a coefficient here, and that's what this one is. So if p is a content of this, phi of f of x is equal to phi of g of x times h of x, and that should be equal to 0, because you have a common factor here, and if you take p outside, the p will be mapped to 0 because it is n mod p. But this is a homomorphism, and that means g of x times h of x is equal to 0, meaning phi of g of x, phi of h of x is equal to 0, which implies either phi of g of x is equal to 0 or phi of h of x is equal to 0, because this is a integral domain. Zp of x is an integral domain, which contradicts. This is a contradiction because we don't want 0 factors. This is a contradiction, and that implies g of x times h of x is primitive. Now let us come to a main theorem. What we need to prove that is, if f of x has factors in q of x, it also has the same kind of factors in z of x. We are going to assume that f of x is primitive, because if it is not primitive, we can take the content outside and make it primitive. For example, if, as I said earlier, 2x squared plus 6x minus 8, this is not primitive, but if you take the content out, x squared plus 3x minus 4, this is primitive. So we are not considering any non-constant, we are not considering constant polynomials. If you can do the theorem for a primitive polynomial, it is also true for a non-primitive polynomial. So we are going to assume that f of x is primitive. So let us assume that f of x is primitive, and f of x is equal to r of x times s of x, where r of x and s of x belongs to q of x. What is the difference between a polynomial in q of x and z of x? The coefficients are rational numbers. So what we do is, we'll make this one as a polynomial in z of x. So let a and b are integers such that a times r of x and b times s of x belongs to c of x, which is possible. So that means ab times f of x is equal to a times r of x times b times s of x, because we are multiplying a and b here. See, f of x is primitive, so if you take the whole thing, the content of the whole polynomial is ab, because this is primitive, right? Okay, now these two polynomials are in z of x. So let c and d be the content of a times r of x and b times s of x. Taking the common factor. So we can write this one as, that is, a times r of x is equal to c times r prime of x, and b times s of x is equal to d times s prime of x, right? So you can write ab times f of x is equal to, here, cd times r of x times s prime of x, where r prime of x and s prime of x are primitive polynomials in z of x. So these two are primitive polynomials. So the product is a primitive polynomial with this result. So this is a primitive polynomial. So this is also a primitive polynomial. They are equal, and that implies AB is equal to CD. And what does that mean? That means f of x is equal to f of x is equal to so that means f of x is equal to r prime of x, r bar of x times s bar of x, and r of x, s bar of x are in z of x, and that completes the. Let us do a corollary of this theorem. Let f of x is equal to x to the power of n plus a n minus 1 x to the power of n minus 1 plus dash 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 plus a0 belongs to c of x, where a0 is not 0. Then if f of x has a 0 in Q, then it has a 0 in Z, and that 0 divides AC. It's a very simple corollary from the previous result. So let alpha belongs to Q be a 0 of f of x, and that implies f of x is equal to x minus alpha times g of x, where x minus alpha belongs to q of x and g of x belongs to q of x. And with the previous theorem, if you can factorize in q of x, you can factorize in g of x, z of x. So that implies f of x is equal to x minus m times g prime of x, where m belongs to c and g prime of x belongs to c of x. So this one will be x minus m times x to the power of n minus 1, because this is of degree 1 less than n, and the coefficient of x to the power of n is 1, and this is also 1, so this has to be 1, plus dash dash dash, and the last term will be a0 by m, because that is the only constant term, and when you multiply it has to be a0. So this implies, and this actually belongs to z of x, and that implies a0 by m belongs to c. That implies a0 by m is a integer, and that implies m divides